Welcome back. In this example, we are going to perform the inverse DTFT, not the DTFT. Inverse DTFT of x omega will give us x of n. And here we'll show you that if we are given this x of omega, which is a rectangle pulse, so the horizontal axis is omega, and we are repeating every 2 pi because remember that x omega is periodic with 2 pi, and this is a square pulse. You realize that the inverse DTFT becomes a sinc function. The other way to look at it is that if you perform DTFT of a sinc function, because this is aperiodic, you get a square pulse. So that's the relationship. Right, let us see what is the inverse DTFT of the square pulse. So remember that this is the inverse DTFT equation, which is 1 over 2 pi integrate of one period, which is 2 pi, of x omega ej omega n d omega. Now, so all we need to do is to plug in what is x omega, and x omega is this pattern over here. And of course, this has finite support. Basically, it is only non-zero at minus pi over 4 to pi over 4. So this integration reduces to here, and b is equals to minus pi over 4, and then positive v is pi over 4. So the only problem now, of course, is how to integrate ej omega n d omega. And remember, if you look at your calculus tables, integrate ejk omega d omega, you basically treat jk as the constant, and you bring 1 over jk down, ejk omega, and that's what we did. So we bring jn down is 1 over jn 2 pi, which was the original constant, and the limits of the integration is from minus b to b, and therefore now we can substitute in here. So b becomes 1 over j 2 pi n e j n b minus e j n b minus. So later on you realize that EJNB minus E minus JNB divided by 2J is sine Bn. Alright? And then leaving us with n pi. Now, we can leave the answer to this, but sometimes we prefer it to be in a sinc representation. So in this step, let us work from this step to this step and see that they are the same. Right, to know this step, please remember the sinc function is defined like this. Sinc k is sine pi k divided by pi k. So the pi is introduced into this variable k. So if we have sinc bn pi, then basically we're doing sine bn pi times pi divided by, then we have bn divided by pi times pi. So we start to remove all the redundant pi's over here, and redundant b over here, and we are left with sine bn divided by n times pi, which is exactly this expression. So in this slide, we perform the inverse DTFT of a square pulse, and we see that it's a sinc. And in fact, if you do a discrete time Fourier transform of a sinc, you'll get a square pulse. Thank you.